In this video, we're going to take a look at section 1.4 on linear equations of two variables. In the previous section, section 1.3, we actually already got a glimpse of this topic. At the end of that section, we talked about finding the x and y intercepts of linear equations, and we talked about graphing vertical and horizontal lines. So we're going to kind of continue, maybe kind of even go back a little bit before that, introduce the whole concept of a linear equation now, and then continue the study of that topic of graphing lines. A linear relationship occurs when two variables, x and y, have the property that changing x by a fixed amount, went the wrong way with that, causes y to change by a fixed amount. So what's happening here, the example I always like to give is buying bananas, because at least it used to be, I don't know anymore, I haven't checked in a while, but bananas were fairly stable in price and were generally about 50 cents a pound. So if you buy, 1 pound of bananas, that's 50 cents. If you buy 2 pounds of bananas, that's $1. If you buy 3 pounds of bananas, that's $1.50. What's happening there is that each time the number of pounds is increased by 1, the total cost changes by 50 cents. And so each time we change the amount, maybe let's put it this way, each time we change the weight by a certain amount, the cost will also change by a certain amount. And so that's a linear relationship. A really good indicator that you have a linear relationship is if you can use the word per to describe it. 50 cents per pound. 20 miles per gallon, like for a car. That would be a linear relationship if your car got exactly 20 miles per gallon. For every gallon of gas you consume, you'll go 20 miles in your car. And so again, it's two fixed amounts. When one changes by a fixed amount, the other changes by a fixed amount. And that's what makes a linear relationship happen. And if you have a linear relationship like the cost of bananas or the fuel efficiency of your car, that relationship can be described with a linear equation, which is what we're going to be taking a look at here in just a few minutes. Whenever you're dealing with a line, one feature of a line is the slope, which visually is just how slanted the line is. Is it a shallow line or is it a steep line? The slope is a measure of how shallow or steep the line is. More technically speaking, the slope is the ratio of that change in y over the change in x. So we just talked about on the previous screen that when x changes by a fixed amount, y changes by a fixed amount. If we take those fixed amounts and take a ratio of the change in the y variable on top, the change in the x variable on the bottom, a ratio just means it's a fraction. That is a measure of the slope of the line. It is a measure of how much y changes with respect to x. Therefore, the slope measures the average rate of change. I don't know if that's a therefore. In reality, sometimes things don't behave perfectly. For example, the fuel efficiency of a car, we might say is 20 miles per gallon, but that varies, right? It kind of depends how you drive. And if you're driving in a city versus on the highway, but also just on your driving behaviors, that can affect how fuel efficient your car is. And even if you are pretty consistent, it might not always be exactly 20 miles per gallon. That's really just an average. And so it's oftentimes the case that we'll take a situation that in reality is a little bit more varied, and we will simplify it by just taking the average change that happens over a certain amount of time. And in that case, if it's the same, or maybe even not over a certain amount of time, but we just take the average amount that it changes by. So maybe sometimes you get 20 miles per gallon, other times you get like 25 miles per gallon, other times you get 18, and we just kind of average it out somehow, kind of weight those different instances, and the average rate of change is often used. And in that case, it becomes a linear equation when we simplify those slight variances by just using the average rate of change instead. So oftentimes the slope can be thought of as the average rate of change. And I want to point that out because there are some word problems at the end of this section And they might use that language. They might say the average rate of change in this case is blank. And that just means that maybe the actual rate of change was a little bit more varied, but we're just going to smooth it out by just taking the average. And once you take the average rate of change, it becomes a linear equation. And then you can treat it like a linear equation, which is what you'll do in those word problems. In graphs, the slope measures the steepness of a line and is thought of as rise over run. All right, so I apologize on some of these I'm not the best at going back and editing things, so you might see typos in my presentations here. I'll try to correct them as they occur. And I guess in rereading this slide, therefore is really probably not the best choice of words there because it's not really related to the previous statement. It's just another way that the slope is, engaged with. I don't know if that's the right way to say that either, but it's just another dimension to the slope. Is that in reality, the situation might not be linear, but we can sometimes simplify situations by looking at the average rate of change instead of the actual rate of change. And that changes it to a linear equation, which makes it just a little bit easier to manage mathematically. All right, anyways, I'm belaboring the point. So let's move on. There's our formula for slope. M equals y2 minus y1 over x2 minus x1. M is the letter that is used to represent the slope. I've heard different things, but I think the most recent thing I've heard is, why does M represent the slope? That's just lost to history. We've lost track of why M was the letter that was chosen for that. So that's last I've heard. But you would think S for slope, right? But it's M. And what we're doing here is we're taking the change in Y on top over the change in X. All right, so this is the definition that we just talked about on the previous screen, right? The ratio of the change in Y over the change in X, change in Y over change in X. And to measure the change, you will subtract, right? So an example I like to give my students in class is if I ask you what was the change in temperature from this week versus last week, for example. So this week, we're kind of getting close to summer, and this week has been actually a lot hotter than it was last week. So this week we're kind of in the 90s. Last week, I want to say we were like in the 70s. So what's the change in temperature there? About 20 degrees, right? We went from 70 degrees up to 90 degrees. And so that's a change of 20 degrees. How do you measure that change? You subtract, right? So it's a very simple operation to measure that change. So if we want to measure the change in the Y variable, we subtract two Y variable values, right? And so we take the Y value at one instance minus the Y value at another instance, and that will give us the change in the Y variable, the change in Y. And we do the same thing with X, right? We want to measure the change in X, so we will subtract the X values at two different instances to find the change in the X variable. The important thing is that we're measuring those changes at the same spots, right? So we're using two Y values to measure the change in Y, and we're using two X values to measure the change in X, but these have to be paired together. So this X2 has to be paired with Y2. So they have to be measured at the same spot, if you will. And same thing with X1 and Y1. So you can't just use two arbitrary X's and two arbitrary Y's. The X's and the Y's have to be linked together, and the measurements have to be taken at the same time. Okay. So for example, bananas, right? So if we buy 2 pounds of bananas, it was $1, right? And if we buy 3 pounds of bananas, it's $1.50 because it's 50 cents per pound, right? So if we think of this as our X values and this is our Y values, we can find the slope here. We'll take Y2 minus Y1. I want to subtract the two Y values. But so again, I could also say, 4 pounds is $2, right? And so what I can't do is I can't say, let's take $2 minus $1 for Y, but then do 3 minus 2 for X. Because if I'm going to use the $2, that's linked with the 4 pounds, right? We have to take the measurement from the same spot, right? So if we're going to use $2 for the value, then we have to use the amount that gives you that $2 as our X value. So make sure that the x's and the y's you used are linked together. They're taken from the same measurement, if you will, right? The $2 comes from the 4 pounds. And so if I'm going to use $2 for y2, that's fine. But then I have to use the 4 pounds for x, right? Because that's what's linked to that $2. And it needs to be in the same order. Minus $1 for y for this particular measurement. And for that one, the x value was 2 pounds. I almost said $2, but it was 2 pounds. And so if you do this calculation, you get 2 minus 1, which is 1, over 4 minus 2, which is 2, which you get 1/2. You might say that's a weird number to get. But if you think of it as a decimal, it's 0.50. And that reflects the 50 cents per pound. That's what this number is actually telling you. So that per that I mentioned earlier, if you see the word per, that's a linear relationship. That's also your slope, right? 50 cents per pound is the slope of that line for that particular linear relationship. All right, so you're going to have a problem on the homework where they give you 2 points and they ask you to find the slope. And at some point, I like to caution my students to be careful here, because if you think about the problems we had in section 1.3 involving circles, there are also problems there that give you 2 points. So you can't assume when you're given a problem that has 2 points what you're supposed to do with it. You can't just automatically know, oh, there's 2 points, so I'm going to do this. You have to read the directions, right? So if I give you 2 points on the test, I could be asking you to find the circle with that center passing through that other point. I could be asking you to find the slope, which is what we're being asked to do here. Or you could be asked to find the equation of a line passing through those 2 points, not just the slope, but the equation. And so there's multiple things. Or distance and midpoint. That was another problem we saw in the previous video, right? If I give you 2 points, I might say find the distance between these 2 points. You have to read the directions to know what you're supposed to do with these 2 points, right? So to find the slope, we're just going to use the formula m equals y2 minus y1 over x2 minus x1. And something else I advised in the previous video for section 1.3 is if you have to plug 2 points into some kind of formula, which is what we're doing here, that you should label those points first before you plug them into the formula. That way you make sure they get to the right spot. And once you've labeled them, then you don't have to really think about, okay, which one should go here, which one should go here. The label will tell you where it should go. So this is our first point. It's an x coordinate and a y coordinate. And because it's our first point, I'm going to put 1s on those. This is my second point. It's an x coordinate and a y coordinate. And because it's the second point, I put 2's on those. And so I plug them in the way they're labeled. So y2 is -8. So I don't even have to really think about it at this point. I just go with the labels, right? -8 there for y2 minus y1, which is -5. All right, so that's what we get on top. On the bottom, we have x2, which is 12, minus x1, which is -2. And then we simplify, and we have several places. We talked about this in the previous video too. Several places with double negatives, so be careful with that. Minus a negative becomes plus. So we get -8 plus 5, which is -3. And then 12 plus 2, which is going to be 14. And as awful of a number as that is, that's the slope for this particular line. That tells me how the y value changes with respect to the x value. Specifically, that y goes down by 3/14 every time x goes up by 1. That's what the slope tells me. It also tells me that y goes down by 3 every time x goes up by 14. You could also interpret it that way. That's rise over run, which is something we're going to talk more about later. All right, this one, I would say, it's the same problem, find the slope. And I do like to, in the videos, have problems where I say pause the video, give this problem a try, but something really odd happens with this problem. So I'm going to go ahead and do this one as well. You can, you're in control. You can pause the video whenever you want and try these problems. But just be aware if you do that with this problem, something weird does happen. And so we'll use the same formula, y2 minus y1 over x2 minus x1. This is x1, y1. This is x2, y2. Plug the numbers in the way they're labeled, so I get -9 minus -5 on top. On the bottom, I get 4 minus 4. And so on top, we get the double negative again, which gives me a plus. And so I get -9 plus 5, which is going to be -4. But what happens on the bottom, in the denominator? We get 4 minus 4, which is 0. And some students will say, okay, so my answer is 0, and that's not correct. So it kind of depends, right? If in your calculation of slope, you get 0 somewhere, there definitely is something significant about that. If 0 is in the denominator, then this is undefined. We talked about this way back in section 1.1. You cannot divide by 0. We have to always avoid dividing by 0 because it just is not a valid mathematical operation. And so here we're given something that's invalid. -4 cannot be divided by 0. There is no result from this. It just doesn't even produce a result. So we say this is undefined. Now, some people might say, oh, there's no slope here, but no slope is too ambiguous. Because when we say there's none of something, we also might mean there's 0 of it, right? And so if you say no slope, I don't know if you mean the slope is 0, which means it exists, but it's equal to 0, or if it's undefined, meaning it just doesn't even exist. The slope doesn't even exist in this problem. So we don't want to say no slope because of that ambiguity. It's just undefined. So if the denominator is 0, the slope is undefined, and that's when you choose option B. If the numerator is 0, so if we had instead got 0 over -4, this is okay. This is a perfectly valid mathematical operation. You take 0 divided by -4 and you get 0. 0 divided by any number is going to be 0, right? And so in that case, the slope would be 0, and you would write the answer for option A, right? So if the slope is 0, that's fine. That's a slope. It exists. It's equal to 0, and that's the answer you type in for the slope. But if the denominator is 0, the slope doesn't exist. It is invalid. There is no, I shouldn't say there is no slope, right? I said don't say that. But it's non-existent. And so you want to say the slope is undefined in that case. All right, so just be on the lookout for either of those possible cases. All right, so here are the formulas for the equation of a line. There are different ways it might be presented or that we might want to work with it. The most common formula, the most useful, is this one here, and the one that you're probably most familiar with, y equals mx plus b. This is called the slope-intercept form. Slope-intercept form for the equation of a line. What's great about this is that there's so much useful information that you can just read directly off the equation without having to do any calculations. We already talked about m. That's the slope, right? So the number in front of x is your slope for that line. You don't have to calculate it. You don't have to investigate or research to find out what the slope is. It's there to be read straight off the equation. I don't know how else to say it. It's given to you basically. You just have to know where to look. And so that's why this form of the equation is really useful, because of that useful piece of information that you just get for free. B is another really useful piece of information. It's often described as the y-intercept, but I think we talked about this at the end of the video for section 1.3. Intercepts are points. And so we don't want to say, oh, B is the y-intercept, because B by itself is not really a point. So to be technically correct about it, what we would say is the y-intercept is 0, comma, whatever that number is for B. So informally speaking, it's very common for people to say this number is the y-intercept. But technically speaking, it should be 0, comma, this number is the y-intercept. And so we're going to try to keep it technically correct. And that's also the way you'd have to type it in the math Excel if they ask you for that information. All right, and so that's the slope-intercept form. It's the one I try to use most often for most cases if I can. But we do have this other form that can be useful, but you'll never see I shouldn't say never. It's really rare for problems to be given in this form. So it's very common for problems to be given in the form y equals mx plus b. Slope-intercept form, a lot of your problems will be given to you in that form. But it's really rare to get problems in this form, and this is called the point-slope form. And the only reason we have it on this list is because it actually is pretty useful for starting out on a problem. So there's going to be some problems where we might start with this formula, plug some numbers into it, and then rearrange it to make it look like the slope-intercept form. So this is a place that you would start, but you would never end with an equation looking like this. It's just not the way we want our equations to look. And then the last one you see here, ax plus by equals c, is called the standard form. Sorry, my handwriting's kind of bad there. Standard form. In fact, I forgot, I kind of changed the thickness of the writing, and this is the thinnest setting, and maybe that's kind of why it's harder to read. I'm looking at this feeling like, oh, my handwriting's really like shaky and hard to read. I think it's because I'm using the thinnest setting for the pencil, and so maybe if I change that, it'll be a little bit easier to read. So I apologize for that. Standard form, which really just kind of means the generic form, right? It's just a generic way of writing an equation, and if it's written in this, if it looks like this, it's still a linear equation. It'll graph as a line, but it's just a generic way of writing that equation. What is nice about this is that the equation will always look nice. A, B, and C must be whole numbers. So these have to be what are called integers, which are whole numbers that could be positive or negative. So A, B, and C have to be integers. Yeah, see, that's better. That's easier to read, I feel like. So I apologize if my writing was hard to read. So these have to be whole numbers. And so if it's given to you in this form, it'll look nice. It doesn't always behave nicely once you start digging into it, but it'll always look nice to start out. And if you have to write your answer in this form, it takes a little bit of work, but you're going to make it look nice. So it's not going to have any fractions. That's by saying that these have to be integers. What we're saying is no fractions in this form of the equation. Okay. So we're saying no fractions in the equation itself. Now, will you have to deal with fractions as you work with that equation? Maybe, but the equation itself will not exhibit any fractions. Okay. So here we're being asked, we're given 2 points again. So I want to go back to this point I was making. You can't just assume, oh, 2 points, I'll just find the slope, because that's what we did before. This time the directions are to find the equation of the line containing these pair of points. Look closely at that, because in 1.3, the question could say, find the equation of the circle with these 2 points, right? And so you have to you can't just say, oh, equation y equals mx plus b, because what if it's a circle? Then it's a different formula, right? So you really have to kind of pay attention to these details in the directions. I find, and we're all guilty of that, right? We're always looking for like efficiency and shortcuts. And so, when you study a math topic, when a problem looks a certain way, you're like, oh, when it looks like that, I'll do this. And we kind of get away from looking at the actual wording and the directions. But you got to be careful with that, especially if you're given 2 points. Got to look at the directions. All right. So there's 2 ways to do this problem. Let me see. Do I have another example after this? Kind of. It's finding an equation, but with a different piece of, different set of information. There's 2 ways to do this problem. I'm just trying to think, do I want to do both of them on this one problem, or do I want to do one way now and do one a different way later? So I think what I'll do here is I'll just do it the one way. And then I'll talk about the other method in a later example. So one way of finding the equation of a line, again, we're talking about a line here, so we need both of those pieces of information, is you can use the point slope form. And this is honestly my least favorite way of doing it, my less favorite way of doing it. I prefer to use y equals mx plus b, and that's probably what we'll use for the rest of the lesson. But I do want to at least make you aware there is another way you can approach these problems, and you might prefer this way. And so it's fine. I'm not saying my preference is correct. It's just my preference. I prefer to use y equals mx plus b, but other people prefer to use the point slope form, and there's nothing wrong with either method. So I want to present both ways so that you can make that decision for yourself. Which way seems to make more sense to you? Which way do you prefer to do it? So you can make that choice. And on the test, I'm fine with either method. All right. Whichever method you're going to use. So let me just kind of at least acknowledge this, that we could also use this formula to do this problem. Either way, to get started, you need to know what the slope is, right? You're not going to be able to really take that first step to finding the equation until you find m. What is m equal to? So this would be a good point to pause the video. So pause the video and then find the slope. You don't have to do the whole problem. We're going to work on the equation together, but we need to find the slope first. And that's just like what we did earlier. So it's really a repeat of the example that I did earlier with finding the slope. But I want you to try it this time. So go ahead, pause the video. I'm going to do the same thing. I'll pause my recording. And then when you resume the video, you should just see the answer on the screen. You can check to make sure that you came up with the right answer, meaning, the answer being the slope, right? So find the slope, pause the video, find the slope, resume the video, and see what the slope is. See if you got it correct. Okay, so here is my work for finding the slope, and I end up with 3/2. Be sure we really haven't seen this happen very often at all, but whenever this should automatically be the case. If you're, if you're dealing with a fraction, especially if it's going to be your answer, you should always reduce it. So in this case, we actually end up with 6/4 initially, but then that reduces to 3/2. So you want to make sure you're reducing that. So that's the slope. So now that we know the slope, we can go ahead and plug that in for m, right? That's going to be our slope. And what's nice about the point slope form, this is why it's still around and it's still used by a lot of people, is it gives you a place to plug in all the numbers that need to get plugged in, which is not the case with y equals mx plus b. You have to do a little bit of a trick to get the information you need for y equals mx plus b. But for point slope form, there's no trick required. You just plug all the numbers in and you have your answer. The other numbers that need to be plugged in are x1 and y1. So we need to plug in some numbers for these two things. And another nice feature about the point slope form is that you do not mess with the variables. You just leave them as x and y. So we don't have to do anything with those at all, which for y equals mx plus b is not the case. You actually have to plug some numbers into those variables, and that can be a little bit confusing. So what's nice about this is you just leave the variables alone, plug in the slope for m, and then plug in a point for x1 and y1. Now we already have a point labeled x1, y1, but you don't have to use that as the x1, y1 in this formula. Either of these points would work. And while I'm tempted to just say, for simplicity's sake, let's just use what we already have labeled as x1, y1, these numbers are a lot bigger than these. And I think it would be a little bit easier on us if, in fact, we use these as, -1 and -2 as our numbers that we plug in for x1 and y1. And so I'm going to go ahead and make that call. So we're going to go ahead and use this point for x1 and y1 for the purposes of finding the equation. I know we labeled it x2, y2 for the purposes of finding the slope, but when it comes to finding the equation, we can use either point as our x1, y1 here. So this x1, y1 is not the same as this x1, y1 up here, if you will. All right, so we can switch it. And I think that's a good idea here because this point, the numbers are just a little bit friendlier looking. All right, and so we're going to plug in -2 for y1 and -1 for x1. So we're going to end up with y minus y1, which is -2, equals m, which is 3/2, 3/2, times x minus x1, which is -1. So please be careful with all these negative numbers getting plugged in and all these double negatives. I'll find students, again, looking for that efficiency. They want to try to do 5 different things at once just to get through the problem as fast as possible. But then you can get, when you're trying to do too much at once, it's easy to make mistakes. You can get careless, overlook something. So just take it one step at a time. And the first thing you should do here is simplify those double negatives. Don't distribute the 3/2 yet. This is a mess. Let's simplify that first, then we'll distribute. Same thing over here. So we're going to get y plus 2 equals 3/2 times x plus 1. All right. Then I will distribute the 3/2. Now you might say, what? So let me kind of back up a little bit here. Once you plug these numbers in, you have your equation. This is the linear equation that fits the description that passes through these 2 points, right? This is the equation that gives me the line that passes through these 2 points. But it's not in a form that we want to leave it in. So you might say, well, once we have the equation, why are we still working on it? Because we want to have it in slope-intercept form. The directions are explicit about that, but as I mentioned earlier, you never want to leave an answer in this form. It's just a mess. We want to try to simplify it. So that's why we want to go ahead and distribute the 3/2. To put it in slope-intercept form just means solve it for y. Y equals blank, and that'll have it in slope-intercept form for you. So before I subtract the 2 over here, let's go ahead and distribute the 3 halves. I get y plus 2 equals 3 halves x plus 3 halves times 1 will be 3 halves again. Then to get y by itself, I'll subtract the 2 to the other side. So I end up with y equals 3 halves x plus 3 halves minus 2. And because that's a fraction, either I need to use a calculator or I'm going to have to take a little bit of time to figure out what's going to happen here. So we need a common denominator. Multiply 2 to the top and bottom. So I already kind of skipped ahead, but because it's a whole number going up with a fraction, I said that kind of funny, but I usually say going up against the fraction, but maybe that's more like multiplication. But whenever you have a whole number interacting with a fraction, it's helpful to think of the whole number as a fraction also. And so I rewrote the 2 as 2 over 1. And to subtract these, I need to have a common denominator. This is a 2, so I'm going to make this one a 2 also by multiplying a 2 to it. And then, so there's a lot of 2's here. And then if I multiply 2 to the bottom, I have to multiply 2 to the top. So I'm going to end up with 3 halves, right? Positive 3 halves. Let me just kind of rewrite that 2 there. Positive 3 halves minus, this will become 4 over 2. And when I subtract those, now that I have a common denominator for them, I will get negative 1/2, right? And I cannot write my 2 for some reason. And so we get 3 minus 4, which is negative 1, over the common denominator of 2. And then this is going to copy down. So we have 3 halves x, y equals that. And that is the equation of the line that passes through those 2 points that we were given. And it's written in slope-intercept form. Now, when you go to type this into Math Excel, do not type in y equals because it's already on the screen. That is a really common mistake. And I feel bad because, students have the right answer and they're typing in the right answer, but they're typing in a redundant piece because part of it was already typed out for you on the screen. So just be on the lookout for that. So in this box, all we would type in is 3 halves x minus 1/2. That's all you would have to type in there. And again, I can't seem to write a 2 today. Okay, so that is finding the equation of a line given 2 points. Unfortunately, there are other situations where we're going to be asked to find the equation of a line where the information gets a little bit more obscure. That's not the case here, actually. So I guess I'm setting up a problem that we're not quite there yet. But here I would say it's a little more clear because they're giving you the graph. In this particular example, they gave us 2 points, which is pretty helpful. But even more clear than that is not only did they give me 2 points here, they actually are visually showing me what the line looks like. Excuse me. And I could use any 2 points I want. I'll use the 2 that they're marking, but you could actually use any 2 points you want here. So for this one, I'm going to use y equals mx plus b. There's a couple reasons why this would be a good choice. For one, it's my preference. It's the way I like to find the equation of a line. But also, you want to use this formula if you know the y-intercept. So remember, b is the y-intercept. And if they're giving you the graph, look at the graph to see if you can spot the y-intercept on the graph. And if you can figure out what it is by looking at the graph, then you don't need to calculate it. You just know what it is. So if you know the y-intercept, you definitely want to use this formula because then you can just plug the y-intercept in for b. We know the y-intercept here because the y-intercept is where the graph crosses the y-axis. And we can see from the graph they give us that the graph is crossing the y-axis at 2. And so again, technically the point is 0, 2, but b is the y-coordinate of that point. It's going to be 2. And so I can just plug that in for b. That's going to be easier than using the point slope form. Now for the slope, we still need to find the slope here. So let's go ahead and copy the x down and the y. We still need the slope. You can use this formula again, just like we did on the last problem, right? If you have 2 points, you can always find the slope using this formula. But if you have the graph, if you have a visual representation of the line, you can actually find the slope a little bit easier by using a concept I referred to earlier, rise over run. And these are not technical mathematical terms. They're actually chosen to get you thinking in the right direction. So rise, you should be thinking vertically. I think of sunrise, right? The sun goes up in the sky, right? So rise is a vertical direction. Run should make you think horizontally. So like you're running along the ground. And so that's why those words are chosen. It's the change in y over the change in x, but the y direction is vertical. The x direction is horizontal. So another way of finding the slope using the concept of rise over run is to look for the change in y over the change in x. I don't know why I put a 0 there. Change in x. All right. Which is the same. It's what rise over run is referring to. And if you have a graph to look at, you might be able to figure out the rise and the run, the change in y and the change in x, by just looking at the graph. So pick 2 points. I'll use the 2 points they've marked for me, and then measure the vertical change. How much is it changing vertically between those 2 points? That's the rise. So how far up or down are you going when you go from one point to the next? Now, for this exercise, you do have to pick a point to start from. So you have to make a choice. What point am I going to start from, and what point am I moving to measure the change in y and the change in x, to measure the rise and the run? So I'm going to start from this bottom point here. So I'm going to start here. I don't know if that's a very good arrow. I'm going to start here. And then to move to that second point, what's the vertical change? What is the change in y? So maybe I should also say that here, vertical change. I don't know, it's too much writing, but it's 2, right? We're starting down here at -2. We're going up to the x-axis. So we're going up 2. That is the rise. That's how far up or down we have to move to get from one point to the next. And then the run, see if I can squeeze that in here, is the horizontal change. How much does the x value change in going from one point to the next? So again, starting from the same point, to move to that point, what's the horizontal distance that we would have to cover? It's going to be 1, right? We're starting at -2, and then we're ending up at -1 on the x-axis. So the change there is 1. It changes by 1. That's the run. All right, so 2 is the rise, 1 is the run. And so we can plug that into our formula for slope. The change in y was +2, and you do have to be careful. Now I picked an example where they're both positive because we're going up, that's positive, and then to the right is also positive. But if we were to go down, that would be a negative change, and we would need to use a negative sign in our representation of that change when we plug it into the formula. So we're going to get 1 here. Let me just finish this thought. And so we get that the slope is equal to 2. Now, you might say, well, it doesn't matter which point I start from. It actually doesn't. We could start from this point, and if we do that, then we actually go down 2, so the change would be -2 for the vertical change. So the rise would be -2, and then to the left one, which would be -1. So it makes a difference in the numbers that you get here, but when you take the ratio, you would take -2 over -1, which would still give you the same answer. So you'll get the same slope either way, even if the details in the process might be a little bit different. So the slope is equal to 2. And so I'm going to plug that in for m. And then that's my equation. It's already in slope-intercept form because that's the formula I used to start out. Okay, so hopefully that made sense. How to find the slope from a graph. You do rise over run. How far up or down, going from one point to the next, how far left or right, and then divide those two numbers to get your slope. Okay, here we're already given the equation and we want to graph it. And so to graph an equation, we already talked about one method in 1.3, which is you can use the x and y intercept. So we actually already were graphing lines in the previous section. They asked us to find the x-intercept and the y-intercept. We found those 2 points. We plotted them, and then we drew a line connecting those 2 points. What it always comes down to for graphing a line is finding 2 points that are on the line. Once you have 2 points, you have the graph. Another way of getting 2 points, instead of using x and y intercepts, which you could do here, but there is an easier way, is to use the slope and a point. So think of this formula, y equals mx plus b. That's what this equation fits, right? So the equation they gave us is in slope-intercept form. That's how we would say that. And by comparing it to that formula, we can see that instead of m, we have negative 8 over 7 in this equation. So as I mentioned earlier when introducing this formula, what's great about equations in this form is that you can just read this information straight off the equation without having to do any work. I don't have to do y equals, so I'm saying the wrong thing. I don't have to do m equals y2 minus y1 over x2 minus x1 to find the slope. I don't have to calculate it. I can see it in the equation. The number in front of x is the slope. And so just by looking, I see that the slope is negative 8 over 7. So what I like to say is I get that information for free if the equation is in slope-intercept form, which is why it's such a great way of writing the equation. So that's my slope. And I also get the y-intercept for free, right? B is equal to negative 7, which tells me that my y-intercept is at 0, negative 7. All right, so there's my slope, and there's my y-intercept. So I already have 1 point, right? 0, negative 7, which is going to be right here. But to graph a line, I need 2 points. Now, sometimes students will think, oh, the slope is a point also, but the slope is not a point. The slope, the analogy I like to use for that is it's like a treasure map, and it's giving you directions on how to find a second point, which is the treasure that you're looking for, right? So we already have 1 point. We need a second point. The slope is a map giving you directions to find that second point. And again, it comes down to rise over run. So we have negative 8 over 7. That's our rise over run. So the top number is the rise, which is the vertical change in going from one point to another. And so the rise is negative 8, which means we will go down 8 from our starting point. And the run is 7, which tells me I will go to the right 7. Now, a lot of students want to say over 7, but that is, again, ambiguous, right? Over could be left or right. So be specific most of the time, because like if, now the slope being negative, I could actually put the negative with the 8 or put it with the 7. My default is to put it with the top number. And then so that can fluctuate. The rise might be up or down, depending on if there's a negative sign there or not. But if you always put the negative sign with the top number, then the bottom number is always going to be positive. So you're always going to the right. So that's generally how my problems tend to work out. I would change that if I didn't have room. So going down 8, I almost run out of room doing that. I don't quite, I'll be okay. But if I couldn't go down 8, like if my graph got cut off at negative 12, well, I don't have enough room in my window to go down 8. So what you could do instead is put the negative sign with the bottom number. And then you're going up 8 and to the left 7. And that would give you room because you have room to go up. That will give you a different point, but it will produce the same line when you draw the graph. So even though the point will be a little bit different here, you'll still get the same graph that you're supposed to get. So in fact, we can do both of these so you can just see that it works out fine. So I'm going to go down 8. So you have to start from a point that you already know is on the line. So the slope only works if you have a starting point. So this really makes me think of, I don't mention it every class, and I just don't know, it's a pretty old movie. A lot of people maybe haven't seen it. I don't know. But it's Indiana Jones and the Last Crusade. And they're looking for the Holy Grail. And the dad has his Grail diary where he's like, wrote down all of his notes from his, research in trying to locate the Holy Grail. And he has a map, which is like the slope. He has a map, like with all these landmarks. But the only problem was they didn't know where to start from. They didn't know what city to start from to look for those landmarks to get to the Holy Grail. And so that's kind of like graphing a line. If all you have is the slope, you have a map, but you don't have a starting point to apply that map to. So you won't be able to graph your line with just the slope. You have to have a starting point, right? And if you remember from the movie, the starting point was the city of Alexandria. I think it was in Egypt or something. But here our starting point is 0, negative 7. We have that. That again was free information from the equation, right? So we get this y-intercept, which is a point that we know is already on the line. That's where we're going to start from. And then we'll use our map to help us find another point. So starting from 0, -7, we are going to go down 8, which takes me down to -15, which is going to be, I'm going to mark it just so I can line things up a little bit. But that's not my point, because I also have to go to the right 7. And so this is going to be hard to do. I might need to go get my glasses, actually. I feel like my eyes are going cross-eyed. See if I can count it out down here. 1, 2, 3, 4, 5, 6. I hope this is right, but it looks like it's about right there. Okay. I think I lined that up good. Okay, so it's at -15 on the y-axis. So I'm saying the numbers backwards. 7, -15. Right. So we get that point. And that's really all you need, because now we have 2 points, right? We had the one we started with, and then we have the one that we found using the map. And that is enough for us to see the line, right? We just connect those 2 points with a straight line, and there's your graph. But just to illustrate that, you could also have done it this way, and you get a different point, but it lines up exactly on the same straight line. We could go up 8. Now I'm at -7, so if I go up 8, I end up at 1. And then to the left 7. And so it'd be just above -7 on the x-axis. And notice how it lines right up with these 2 points here. So either green point would produce the same graph when you connect it with a straight line. So it doesn't matter which one you have. All right, so let me go ahead and try to draw this straight line connecting these 2 points. I guess I'll use red. I'll start from, I said 2 points, but really we have 3. And so it'll look something like this. On Math Excel, once you, okay, that's not good. Now, the thing I'm trying to do here is the graph doesn't just stop at that point. It also continues this way, but I want to try to at least make it look like it lines up okay. Okay, no, it went a little bit off, but you get the idea. On Math Excel, you plot 1 point, and then when you go to plot that second point, automatically draws the line for you, so you don't have to draw it in yourself. Okay. And so that's how you graph a line using the slope. So now we have 2 methods for graphing lines. Using the x and y intercepts, that gives you 2 points. And using the slope and a point, which will give you 2 points. All right, so the last topic, and then we have some word problems. So we're almost at the 50-minute mark with this video. With chapter 1, I'm afraid, now there are a couple of shorter sections, but like when I'm teaching this in class, like it's hard to get one of these lessons done in one class period, which is 50 minutes. So these videos, now usually the videos go a little bit quicker. They used to for me, like, I don't know, it's kind of new territory for me. I did my intermediate algebra videos first, and those went by a lot faster than they do when I'm teaching it face to face. So I thought the same would hold true for college algebra, but either I'm just not focused enough, because like I'm doing right now, I'm going off on a tangent. But I just wanted to apologize. That's what I'm trying to get at, that the videos are fairly lengthy, and I'm hoping it's just an artifact of chapter 1 being full of a lot of material, because it's trying to review a lot of different topics. Hopefully, as we move into chapter 2, I'll be able to manage the video links a little bit better. So 2 more topics. We have parallel and perpendicular lines, and then we have a word problem to look at. 2 lines are parallel if they never intersect. The only way 2 lines would never intersect is if they're slanted. Let's see if I can do this. If they're slanted exactly the same. All right, so if they're slanted exactly the same, then they would never intersect each other. And if they're slanted exactly the same, then their slopes have to be the same, because the slope measures how slanted the lines are, right? And so the slopes are equal for 2 lines that are parallel. If 2 lines are parallel, the slopes are equal. The slopes are equal, the 2 lines are parallel, right? For perpendicular lines, those are 2 lines that intersect at a 90-degree angle. So kind of one of my, I don't want to say I'm not really trolling my students, but something that I like to ask every semester when we talk about parallel and perpendicular is, we'll talk about parallel, everybody's good with that. Most people seem to already know all the details. Like, they're lines that never intersect, the slopes will be the same. Everybody's good with that. Then before I put it on the screen, I say, so what are perpendicular lines? And oftentimes the answer I'll get is, well, those are 2 lines that intersect. But that's not really special enough to be given a special name like perpendicular. Because if they're not parallel, they will intersect. Their lines intersect all the time, right? It's special when they don't, so we have a name called parallel for that. But it's pretty common that they do, right? Most of the time, if you pick two random lines, they're going to cross each other at some point. What's special about perpendicular, excuse me, is that they intersect at a 90-degree angle. So it needs to be a little more special than just they intersect. They intersect at a 90-degree angle, which means which means they're perpendicular, but that's what we're trying to define. Which means, like this. Like the example I always give is the angle at which the ceiling meets the wall, right? This is a 90-degree angle, right? Now, this one's a little harder to justify. Parallel's pretty easy. For them to not intersect, the slopes have to be the same because the lines have to be slanted exactly the same. For perpendicular, the slopes are negative reciprocals of one another, which means that if you multiply them together, you always get -1 if the lines are perpendicular. If you multiply the slopes together, you get -1. And that's a good way to double check, right? So if you want to know if two lines are perpendicular, take their two slopes, multiply them together, you should get -1 as an answer. If you don't get -1 when you multiply the slopes together, they're not perpendicular. Another way to think of negative reciprocal is reciprocal means taking a fraction and flipping it over, right? So for example, let's say we have 2/3. Okay, sorry, I need to switch back to the pen tool. Let's say we have 2/3. The reciprocal of 2/3, let's draw an arrow here, is going to be 3/2, right? That's what reciprocal means. You take a fraction, flip it over. Negative reciprocal means they would also need to be opposite signs. So if we have positive 2/3 as one slope, then the negative reciprocal would be -3/2. You have to flip the fraction over and have the opposite sign for them to be negative reciprocals. So if I had two slopes, if I had two lines with these two slopes, these lines would be perpendicular because these are negative reciprocals of each other, right? Kind of the relationship works in both directions, right? They are negative reciprocals of each other. And if I multiply these two numbers together, what do you get? Right? The 2's cancel out, the 3's cancel out. You get 1 times -1, which is going to be -1. Okay, so that's what makes them perpendicular. Why does that relationship cause them to intersect at a 90-degree angle? That's a little bit harder to explain, so I'm not going to. Usually I try to give that backstory, and it's something I remember thinking of here and there throughout my teaching career. And at one point I had a grasp of it, but it was pretty complicated. So I'd never really incorporated it into my teaching, and I've forgotten, the justification for it. So I really couldn't explain it to you right now. If I wanted to, I'd have to think about it for a while first. All right. Anyways, write an equation in standard form. We will deal with that at the end of the problem. So don't worry about that yet. Standard form, remember, was ax plus by equals c. So this time we want to write our equation like that. We will talk about how to do that once we get to the end of the problem. Whether you want to write your answer in slope-intercept form or standard form, I don't know, maybe there's a method that works, but I've never done it this way. To find the equation of a line, you always start with either slope-intercept form or point-slope form. You don't start with standard form. That's not a very easy starting place for finding the equation of a line. Even though we want our answer in standard form, we're not going to start with that formula. We're going to start with y equals mx plus b. But you could also start with y minus y1 equals m times x minus x1. Right? You could start with point slope form. My preference is y equals mx plus b. So I'm going to be starting with this formula first. And then once I get the equation in that form, then I will transform it into standard form. All right, so write an equation in standard form using only integers for the line described below. Use the smallest possible positive integer coefficient for x. I don't know if that's really necessarily a requirement of standard form. I don't really think it is, but it's a requirement of Math Excel, probably for just being able to check your answer. So they want the coefficient of x, and positive smallest is not really a problem. We're going to do it in such a way that we'll have the smallest possible number there that we can. But what sometimes has gotten me in the past is making sure it's positive, because I don't really think it needs to be for standard form, but that's what Math Excel is asking us to do. So we'll talk about that when we get to it. And then sketch a graph. I don't know if we're going to take the time to do that. This video is already getting kind of lengthy. So now this time, instead of giving us 2 points and asking us to find the equation of a line from 2 points, they're giving us a little bit of different information. The description they're giving me is this. We are looking for the line that is parallel to 7x minus 2y equals 14 and contains the point 3 comma 4. So that's the line we're looking for. They're giving us the equation of this line, but we're looking for the equation of a second line. So I find that students, the first thing they struggle with on this type of problem is understanding that there are two lines involved. If you are going to use the word parallel, that is a comparison of two different lines. And so you can't use the word parallel without having at least two lines involved in that description. Right? So the first thing you have to realize is you're actually dealing with two lines in this problem. One you're looking for the equation of, the other you're given the equation of already. Right? So what I like to do with this information, and this seems to really work well for students to organize it like this, because as a teacher, there's multiple ways you could approach this problem, but you're not sure what's going to be the most effective for your students to understand how to do it. And so the first few years I remember really struggling with, well, how do I, organize the work here so that my students can follow along with it? And what I eventually developed was this. It's nothing sophisticated or anything, but this was not the way the book did the problem, but this is kind of what I ended up coming up with, is making a chart, a table, to really emphasize that there are two different lines here that we're dealing with, right? There's the line we're looking for the equation of, and I've just kind of taken to the habit of using a question mark as the heading for that column. So this column is for all the information regarding the line that we're looking for the equation of. We don't know this one. That's why it's a question mark. We don't know it yet. And then there's the line we're given the equation of. So I'm just going to use the description given. So for the line we're given the equation of, we write the equation here. We have 7x minus 2y equals 14. Right? And if they give you the equation, which is in standard form, by the way, they give you everything. I mean, really, if you have the equation, you could know anything you want about the line from that equation. You might have to work for that information, but everything that we need to know about that equation can be found from that. I'm saying the same thing twice. Anything we want to know about that line can be found from that equation. That's a better way to say it. I was about to say anything we could want to know about that equation we can find from that equation, but that sounded a little bit silly. All right. Now for the equation that we're looking, I'm saying equation again, for the line that we're looking for the equation of, what do we know about this? Well, we know it contains the point 3 comma 4. So what I'll see students do who aren't really familiar with this kind of problem is they'll take 3 comma 4 and they'll plug it into this equation because they're like, well, there's a point, there's an equation. I will plug x equals 3 and y equals 4 into that equation and see what happens. And what ends up happening is just nonsense. You end up getting a number on one side and you have 14 on the right hand side, and it'll be two different numbers because 3 comma 4 is not a point on that line. It's a point on the line that we're looking for the equation of. It's not a point on the line that we already have the equation of, right? And so you put it over here in this column. So don't do this. That point doesn't go to that equation. It goes to the equation that we're looking for. So it goes in this column. And then the last piece of information we know is that these are parallel. And so I like to write that information up here. So that was probably the hardest part, was like, what do I do with that piece of information? So I eventually decided, put it above the table, that we know the relationship between these two lines is that they're parallel with each other. Now, we're looking for this equation over here, which means I'm going to use this formula, y equals mx plus b, to help me find this equation. But what do I need to know first to get started? Right? We talked about this earlier in the video. You need to know the slope. To find the slope, I need 2 points. That's how we did it before, but I don't have 2 points. They only gave me 1 point. So that's where we're running into some difficulty here, right? So if we had 2 points, we'd be fine. We would just use this formula. I said y again. M equals y2 minus y1 over x2 minus x1, right? But this formula only finds you the slope if you have 2 points to work with, which we don't. So instead, what we have to do is use this other equation to help us figure it out. I can find the slope of this line using the equation that they gave me, use the fact that it's parallel to help me find the slope of the line that I'm looking for the equation of. Now, how do I find the slope of this line? Well, you might say, oh, you could find 2 points, which you could do. Sometimes students will do that. It's not the best way to do to find the slope, but it can work if you're if you're out of ideas and in a pinch. Just get 2 points from that equation, and then you can plug it into that formula. You'll get the slope that way, but it's a lot of work and not the easiest way to do it. The easiest way to do that is to write this equation in slope-intercept form. So rearrange it. It's in standard form. Rewrite it so it's in slope-intercept form, and then you can just read the slope right off the equation. To get it in slope-intercept form just means we have to solve it for y. So the first step there is to subtract the 7x to the other side. So I'm going to continue the work over here. So we get negative 2y equals 14 minus 7x, and then divide by negative 2 on both sides. And so we get y by itself. Now, if you just kind of leave it at that, you get this kind of, I would say, clunky equation that doesn't really, it's hard to interpret. It's hard to extract that information that you want to extract. You don't want to leave it as one giant fraction because the formula that we're trying to match it to is not one giant fraction. So what you need to do is take the denominator and split the fraction up into 2 separate fractions, because that's what you have in your formula. You have 2 separate terms. I need to see my equation as 2 separate terms. So you can take this 1 fraction and split it up into 2 separate fractions. You get 14 over negative 2 minus 7 halves over negative 2. And then you simplify. And so we end up with y equals, this will be negative 7, which I actually really don't care about, but that's what it does simplify to. Here we get minus a negative, which is going to make that positive, 7 over 2, and then we write the x to the side. So it's just rearranging that fraction so it fits the formula a little bit better. So now we can find the slope. The slope, remember, now sometimes students will say, oh, the slope is the first number, so the slope is negative 7. The slope is not necessarily the first number. It depends how you set up the equation. What is always the case is the slope is the number in front of x. So here's x right here. The slope is the number in front of that. So the slope is 7 halves. That is the slope of the line that I was given. Now, I know because it's parallel, this might seem a little bit redundant or unnecessary, but I think conceptually speaking, this is the way you need to think about this problem. Because if it's perpendicular, it does make a difference. So think about it this way, right? The slope of the line I was given is 7 halves. It's parallel to the line that I'm looking for the equation of. So what is the slope of the line that I'm looking for the equation of? Well, for parallel, the slopes would have to be the same. So we would say that the slope for this line needs to also be 7 halves. So I'm writing it again for this column, right? So over here, the slope is 7 halves. And then I use this reasoning to help me figure out the slope of the other line, which happens to be the same slope because they're parallel. But I would say write it a second time because you really want to emphasize that you understand that there are 2 different lines here, right? And so we're going to write the slope twice, once for each line, even though the slope ends up being the same number for both of them. I just think you're better off thinking of it that way and just and showing, how do I want to say, like, not just thinking about it that way in your head, but having it displayed that way on your paper. I think it's beneficial. I find students are better off on these kind of problems if they take the time to write that slope a second time, even if it's the same number. Okay, so now we have the slope of the line that we're looking for, the equation of. So we can go ahead and plug it into that formula. So from here, the problem is just like what we did earlier. So once you have the slope and you have a point, actually, we didn't do a problem like this earlier. So if you were doing this point slope form, it'd be just like what we did before. Here's your value for m. This would be your x1 and your y1. Plug those numbers in. It's just like what we did before. What I didn't do earlier was an example using this formula for finding the equation of a line. So let's go ahead and do that for this one. So we're going to have y equals, we'll plug in. So what you do first is once you have the slope, plug it in for m. So we get 7 halves x plus, now b is the y-intercept, which we do not know. A common mistake I'll see students make on the test is they'll say, okay, the slope is 7 halves, And then b is y, and so that's a 4 in this case. So they'll put 4 here for b. That is not correct. B is not just some random y coordinate. B is the y-intercept. It's a very special point. It's the y-coordinate of a very particular point, which we do not have. We're not given that information. How do I know this is not the y-intercept? Because the x is not 0, right? For the y-intercept, it needs to be 0, comma something. If the point I was given was 0, comma something, then yes, that's my value for b, and I could just plug it in for b. But this is not the y-intercept. The x-coordinate is not 0. So b is not equal to 4. That's what I'm trying to get at. All right. We don't know what b is equal to. So if you're going to do the problem this way, using the slope-intercept form, you just leave that as b. If you don't know what b is equal to, just write b there still. Then to find b, you take the point you were given and plug it in for x and y. So here you're going to have to kind of mess with the variables. I'm temporarily going to plug in 3 for x and 4 for y. This is only temporary, just long enough so that I can solve for b. And once I know what b is equal to, I revert back to having my variables. I'm going to reset it back to x and y. But I need to find b first before I do that. So I'm going to plug in 4 for y, and I'm going to plug in 3 for x. And by doing that, by plugging this point in for x and y, the only letter left in my formula is b. So now I can solve for b and find out what b is equal to. So again, fraction going up against a whole number. So think of the whole number as a fraction also, so that everything kind of lines up nicely. When you're multiplying, you do not need a common denominator. You just multiply straight across. So you're going to get 4 equals 21 over 2, right? 7 times 3 is 21. 2 times 1 is 2. And then we need some more room here, so I'm just going to scroll down. Solve for b by subtracting the 21 over 2 to the other side. And because it's a fraction and we're dealing with a whole number here, we're going to have to take our time with it. Or if you have a calculator that does it for you, that's great. Plug that in your calculator and you're going to be all set. But I'm just going to write it out and do this by hand. Right. So I subtracted the 21 over 2 to the other side. So b is equal to 4 minus 21 over 2. Again, whole number, fraction. So think of the whole number as a fraction also. This time we need a common denominator to subtract these. And so I'm going to get a common denominator, same as last time. We're going to make this a 2. And so we're going to get 8 over 2 minus 21 over 2 equals b. Now we can subtract these. 8 minus 21 is negative 13. And the common denominator stays the same. It's 2. So the y-intercept was actually negative 13 over 2. That's the y-intercept for this particular equation. It wasn't given to us, right? They gave us the point 3 comma 4. That wasn't the y-intercept, but we just calculated the y-intercept. The y-intercept is 0 comma negative 13 over 2 if you want to write it out as a point, which you don't need to do. What you do need to do is take this value. Now you have some new information, plug it back into the formula so you can get your equation, right? And so I'm going to rope this off here. So we get y equals 7 over 2x minus 13 over 2, right? I'm plugging that in for b. I'm going back here where my variables are, right? Because I'm done with 3 and 4. I used them long enough to find b, and I'm done with them. So I'm reverting back to using variables there because my equation needs to have variables, right? X is not permanently equal to 3. X should be able to equal different numbers. It's a variable. It varies, right? So once you're done with these numbers, go back to having the variables there instead and use this new information you were given to complete the equation. Right, so we plug that in for b and we end up getting this. So this is the equation of our line, but it's not in standard form. So we have one more. This problem's already lengthy and tedious and has a lot of details to it. And they throw this one extra detail. So I don't know if you can tell, but I really don't agree with having to write the answer in standard form. I just don't see why that would need to be necessary, especially for a problem like this where it's already fairly lengthy. But I have no control over it. Math Excel, it's hard-coded into the problem. So I want you to do problems like this, and standard form just comes along with it. I can't change that. So to put this in standard form means I want the equation to look like this. ax plus by equals c. The first thing to make it look like this that you want to do is get x and y on the same side of the equation. So I'm actually going to take this 7/2 x and subtract it to the other side. And I'll go ahead and put that first. So I'll have negative 7/2 x. That's a positive y, so I'm going to put plus y equals negative 13/2. Again, I'm not writing my 2's very well today. Now that's better, right? It really, if you don't know more about it, you would say, okay, that actually matches the formula, right? You have ax plus by equals c, right? Kind of matches the structure of that formula. But remember, a, b, and c have to be integers, which means they cannot be fractions. So this actually does not qualify as standard form because these numbers are fractions. So how do we eliminate the fractions from an equation? We did this back in section 1.1. So we've actually already experienced this situation. I don't know how to say it. We know what to do because we've encountered this situation before. How do we get rid of fractions from an equation? You multiply both sides by the common denominator. And in this case, the common denominator is pretty easy to determine. It's just 2, right? It's the only denominator we have. They're both a 2. So you multiply the common denominator of 2 to both sides of the equation. I'm going to distribute it. And remember, you don't just multiply it to the fractions. You multiply it to every term. I don't know, I just get squiggly there for some reason. You multiply it to every term on both sides of the equation, whether it's a fraction or not. So when we multiply it here, think of this as 2 over 1. The 2's are going to cancel out, and we'll get negative 7x. Right. So we get negative 7x, fraction's gone. But the 2 also has to get multiplied to the y. So we get 2 times y, which will give me plus 2y. On the right-hand side, the 2's cancel. Think of this as 2 over 1. The 2's cancel out. You get negative 13. Right. Now, in my book, this counts as standard form. It has the right structure, ax plus by equals c, and there's no fractions. But the directions were very explicit. They want the coefficient of x to be the smallest whole number possible, which it is, and they want it to be positive. So if I plug this into Math Excel, it actually counts it wrong, which kind of, a lot of people complain about a lot of things with Math Excel, and I think there's arguments to be made against some of those complaints. But there are some little things here and there that I do agree with. And this is one where I feel like it's the right answer, and they're being a little bit picky about the way it's being typed in my opinion. So we don't want this to be negative. Now, we could have avoided this, situation if we had multiplied by negative 2 to both sides. So if your x is already negative, you can switch it back to positive by multiplying by negative 2. Or if you get to this point and you forgot to do that here, just multiply negative 1 to both sides. Either way, we'll end up with the answer we're supposed to get. Just make sure you multiply it to both sides. And you have to distribute it here. So what we end up getting is positive 7x minus 2y equals positive 13. And that's in standard form and with a positive coefficient for x. And then they want us to graph this equation. So maybe that is something worth talking about, because if you're going to graph this equation, and you're going to graph it like we did the earlier equation in this video, this one is not very amenable to graphing. The y-intercept is a fraction. It's negative 7.5 if you want to write it as a decimal. Either way, oftentimes Math Excel will not let you plot points that are decimals. They have to be whole numbers in order for you to plot those points. So the y-intercept is a fraction, and then if you use the slope on top of that, the other point you get will also have fractions in it as well, or decimals, if you will, and may not be something you can graph on the Math Excel graphing tool. So really, graphing this equation the way we did earlier by using the slope is not going to be the best approach. Even if you use this form of the equation, you might say, let's just use this one, and we could do x and y intercepts. That's a good idea when the equation is in this form, except that, again, you're going to run into fractions, right? The y-intercept is going to be 13/2. The x-intercept is going to be like 13 over 7, right? And that's going to be even more difficult to graph. So what you should do instead is not actually graph it from looking at the equation. Go back to where you had a nice point to work with, which is this point here. I would use this point to graph this equation. It's a nice point. There's no fractions. There's no decimals. 3 comma 4. So I'm going to do this really quick here, so it's not going to look pretty, but 3 comma 4 is an easy one to graph. And then that's 1 point, right? And so, earlier, if I go back to that previous page where we talked about this, we use the y-intercept as 1 point, and then we use the slope as a map to help us find additional points. The slope works from any point that is already on the line. It doesn't have to be the y-intercept. So a lot of students get it in their head that the slope only works if you're starting from the y-intercept. That's not the case. You can start from any point that is on it just has to be a point is already on the line. It doesn't have to be on the y-axis. And so we can do this here. 3 comma 4 is a point we already know is on the line. We can use that as our starting point and then apply the slope as our map to help us find a second point from there. And so the slope, we think of it as rise over run. So this is going to be up 7 and then to the right 2. And that will help me find a second point. And so I don't know if I have enough room actually to go up, but we'll just, like I said, it's not going to look pretty, but I'll just go ahead and do that. So we're going to go up 7, 4, 5, 6, 7, 8, 9, 10, 11, right? So we're starting at 4, we go up 7, that takes us up to 11. And then to the right 2 is going to carry me over to 5, right? Because I'm at 3. If I go to the right 2, I'll be at 5. And then, okay, I can at least maybe use the straight line tool for that part. And then you connect those 2 points with a straight line. All right, so for graphing, it might be difficult to do from the equation directly. Go back to the other information that was provided in the problem. They gave you a nice point to begin with. Use that to help you graph the line instead of the equation directly. Okay. All right, so I have just a couple more examples, 2 more pages. I know that we're already at the 75-minute mark, so I apologize for the length of this video. This problem is very similar, but I wanted to do one more of this type because this time it's perpendicular instead of parallel, just to kind of show you the difference there. But, so while I'm pointing that out to you that it's the same problem that we just did, except this time they're perpendicular. So I want to draw your attention to that. I want you to pause the video, give this problem a try, approach it the same way we just did the last problem, except that when you go to find the slope, you want to use the fact that they're perpendicular instead of parallel. So that's going to change what the slope looks like. But otherwise, the rest of the details of the problem should be exactly the same as what we did before. So give this problem a try yourself first. Pause the video and then resume it. And I'm going to do the same because, again, just to kind of maybe shrink down the length of this video, I'm going to pause my recording, work it out without recording myself working it out. And then you can just compare your work to the work that you see on the screen to see if you had the right idea. Okay, so here is the work on this problem. I'm sorry, it's kind of a mess. So we start over here on the right-hand side by setting up the table, writing in the information that's given, 2 comma negative 3 for the line we're looking for, the equation of. Y equals 2/3 x plus 3 for the line we're given the equation of, and that the 2 lines are perpendicular. This one I gave as a problem for you to try, and part of this was kind of chosen for that reason, because there are some parts of this problem that make it a little bit easier, even though it's perpendicular. One is that this is already in slope-intercept form, so you didn't have to solve it for y. It was already solved for y. So right away you get the slope, which is 2/3. However, the slope you want to use in finding this equation is not 2/3. It's negative 3/2, right? Because we want these lines to be perpendicular. This slope needs to be the negative reciprocal of this one. So you flip it over, take the opposite sign, and that's the slope you want to use for this line that you're looking for the equation of. And so once we have that information, I come over here and start with y equals mx plus b, because that's the way I prefer to do these problems. Plug in negative 3/2 for m. And then temporarily, we're going to plug in the point that they gave us for x and y. So 2 for x, negative 3 for y, which is what I'm doing here. 2's cancel out. And what you end up finding, again, another aspect of this problem that makes it a little bit easier to manage, is that b is equal to 0. So now that we know the y-intercept is 0, we plug that in for b, which is what I've done here. That just drops away because it's 0. And we end up with this as our equation. So this is the equation in slope-intercept form. But remember, the directions say write the answer in standard form. So we add the 3/2 x back over, And because nothing is left here, it's going to be a 0 on the right-hand side. And we have to get rid of the fraction, right? Because in standard form, there's no fractions. So you multiply 2, the common denominator, to both sides, and you end up with this. So what you should have ended up with is 3x plus 2y equals 0. That would be the equation in standard form. All right, one last problem to look at. It's a word problem. Jessica gives a walking tour of a popular tourist city to one person for $37, right? So she advertises, I'll give you a tour for one person. You just have to pay me $37. To increase her business, however, she would lower the price by $2 per person for each additional person on the tour. So she says, if 2 of you would like a tour, I will charge each of you $35. I'll knock $2 off the price. If you want to go by yourself, it's $37. But if you will be willing to go as a pair, since there's 2, I will knock $2 off the price and just charge each of you $35. It's a win-win because each person pays less than they would if they had just gone on the tour alone. And it's more money for Jessica because now instead of just $37 for one person, it's $35 from both people, and now she's going to have $70. And that continues. So if 3 people were to take the tour, she would again discount another $2. And so 3 people would each only have to pay $33. So it might be helpful actually to make a chart of what's going on here, right? And so we have the number of people on the tour and how much money each person would have to pay. For one person going alone on the tour, they're going to pay $37. For 2 people, the discount is $2, and so they would each pay $35. For 3 people, there's another $2 discount. They would each pay $33. For 4 people, each would pay $31. And you can calculate how much money she would make in each of these instances, right? $70 here, $99 here, $124 here. So it's, it would increase her revenue as well as giving a discount to people. And this one's only $37. Now, it's kind of an interesting situation to explore as far as if you wanted to know what number of people would maximize the revenue. So I'm sorry, I know we're trying to get to the end of this video, but there's this really interesting aspect to this problem, which is at some point, this price is going to drop really low. So let's see if we can kind of find where that point would be. Like, let's say, for instance, if 16 people were taking the tour, right? That's 15 $2 discounts, right? Because that's when you're at 2, that's one $2 discount. When you're at 3, that's 2 $2 discounts. So 16 would be 15 $2 discounts, which means $30 off the price. So each person would only be paying $7. Now, in that case, maybe that's still a good deal. Let's see. So 16 times 7, how much is that? 42. That's only 112, right? So think about that. Jessica would make more money if only 4 people take the tour versus if 16 people take the tour, right? She actually ends up losing money if she has 16 people on the tour than if she limited it to just 4 people, right? And it gets even more extreme. So if we went a little bit further, like a couple more $2 discounts, I'm really trying to find the sweet spot here. I think maybe 19, right? That'd be 18 to, yeah. So if 19 people took the tour, according to this formula, each of them would only pay $1. And in that case, she only makes $19, right? And that's worse than if only one person took the tour. And the other aspect of it is, like, even for $112, 16 people is a pretty big group to manage. And you wouldn't want to be like making less money having to do more work, right? Which is what would end up happening. And so there's a point at which the revenue for Jessica is maximized. So there's a certain number of people that she really would want to target as the sweet spot for how many people she wants on the tour, which is a whole different question that we're not being asked to address, but it is a question that you would look into for calculus. So just my sales pitch for calculus. If you think that question's kind of interesting, where would the revenue be maximized for this scenario? That's what, there are tools in calculus that would help you answer that question. And so I'd recommend taking that class. All right. So let's scroll back up here. All right. Now, we don't really need quite that much information. Write the cost per person C as a function of the number of people in on the tour. So this is a really common phrase in math. X as a function of y, or y as a function of x. In this case, we want c as a function of n. And what that means, we're going to talk more about functions in chapter 2, but essentially for now, you can just think of it as meaning you want an equation. A function means you want an equation. It's a special kind of equation, but you want an equation that's solved for this variable. So you want to have an equation involving c and n, and you want it to be solved for c. And just to really drive that point home, on the screen for Math Excel, they make it pretty clear here. You want c equals something. You want an equation where it's c equals something involving n. Right? Now c is the cost per person, which is this column here. So c is like our y variable, and n is the number of people on the tour, which is this column here. Now it doesn't say that this is a linear equation that we're looking for, but you probably know that because it's in section 1.4, which is on linear equations. So just by virtue of it being in this section, you know it's going to be a linear equation. But you also should know this for a couple of reasons that we talked about earlier. Each time one variable changes by a fixed amount, the other variable also changes by a fixed amount. Each time n goes up by 1, the cost per person goes down by 2. That makes it a linear relationship. And the other thing I pointed to that you should be on the lookout for is this word per, right? So either of those two things are clues to you that this situation is linear. And if you know it's linear and you want to find the equation for that linear situation, the first thing you should think of is the formula y equals mx plus b. We're trying to, like, this problem is no different than the problems that we were doing earlier in this video. We're trying to find an equation of a line. That's all we're trying to do. Even though it's a word problem, it's really just a problem of finding the equation of a line. And to do that, we're going to start with our formula, our preferred one. Now you can use the other one if you want, the point slope form. I prefer the slope intercept form, so I'm going to use this formula. Except we do need to make a couple modifications. We don't want to use x and y, right? That's the generic formula, or sorry, not formula. That's the generic variables that we use in the formula, but those can easily be swapped out for other letters if we so choose. And in this case, we didn't choose, but the problem chose for us. Instead of y, we want to have c, right? Again, because we want c as a function of n, we want c equals some equation, which means we want, instead of y here, we want c equals, right? And instead of x, we want n. But the m and the b can stay the same. M is the slope, b is the y-intercept. Now, I'm going to go ahead, because we're reaching an hour and a half. Let's see if we can get done before we hit that mark. The shortcut here. Now, you could find the slope using 2 points, right? You have 2 points here, right? Each entry on this table is a point. 1, 37 right here. This is 2, 35. You can think of these as points and then use the formula y2 minus y1 over x2 minus x1 to find the slope. But I mentioned earlier in the video that another way the slope is described, because we talked about bananas, right? 50 cents per pound. That 50 cents was the slope. So whenever you see the word per, that number associated with that word is the slope of your linear equation. So my slope here is actually the $2. So I don't actually need to calculate it. They actually tell me in the problem what the slope is. It's 2. But you have to be careful about this. It's going to be -2 because the price is decreasing. She is lowering the price by $2 per person. So it's actually a drop of 2 each time n goes up by 1. And so it's given to us in the problem, but you do need to be careful about the sign of that slope. And that's something else you would need to think about. Now for banana, I'm already going to go past the 1 hour and 30 minute mark. I'm sorry. For bananas, 50 cents per pound, that's positive because the cost is increasing by 50 cents. It's going up. So it's a positive 0.50. But here, the cost per person is decreasing. So it's a negative slope. So -2. And then I might still be able to make it, for the y-intercept. Remember, that's when the x-coordinate is 0. So the pattern here is pretty clear that each time n goes up by 1, the cost is dropping by 2. But we can reverse that. If we decrease n by 1, the cost goes up by 2. So if I go backwards from 1 back to 0, then what's going to happen in the right-hand column? It would reverse from 37 back to 39, right? Because that's what the pattern is. It's a difference of 2. It would go back up 2. And so we get the point 0, 39. And so that's my y-intercept. So that's my value for b. So b is 39 in this case. However, if that doesn't make sense, you can calculate it by just leaving it as b and then taking one of these points and plugging it in, right? Plug in 37 for c, plug in 1 for n, that's one of our points, and then solve that, and you would get 39 for b that way if you wanted to check it that way. And then you plug it into the formula, and so you end up getting this. Then the question asks, so that's the equation. Now, if this problem's on my exam, if you're one of my students, this is really the main point of the problem, is finding that equation. So sometimes I'll get students that skip this part and they just answer the question at the end. That's really the minimal part of it. Like, that's not that important to me. The important part to me of this problem is that you can construct this equation. And that's worth like 4 points on the problem. And then answering this question is just like 1 point. So I'll give you some credit for answering it, but it's not the main focus of the problem. So don't make it your main focus of the problem. Don't think, oh, the equation doesn't really matter. I just need to answer this question. The equation is really what matters here, not this question so much. All right, how much does she make on a tour with 6 people? So we can use this formula to find out how much she would charge per person, right? By plugging in 6, right? So they want 6 people on the tour. We'll plug it into this equation. Instead of doing this chart over here, we can just calculate it using the equation. So I get negative 12 plus 39, which is going to be not negative. It's going to be 27. And so that means she would charge each person $27, right? So again, that's the cost per person. And so how much is she going to make? We'll have to multiply 6 people, each paying $27. That's going to be 42. And this will be, what did I do? All right, 12, 162. So it looks like she would make $162 in that situation. All right, so I'm going to go ahead and conclude the video as quickly as possible. Thank you for watching, and I will see you in the next video that will be on section 1.5.